Hello and welcome to the lecture number 10 of Physics 401A. In this lecture, we will basically continue the thematic of our last lecture, which was to guess the form of the Lagrangian of a free particle and a system of particles which are also free and can also be interacting, right? So according to the discussion till now, what we could say that inertial frames are such frames of reference according to which the space and time both are homogeneous and time is also, space is also isotropic. In addition, we also defined Galilean relativity, and also we said that all the inertial frames of reference, they they can move with respect to each other by a uniform velocity, okay, and they are the motion of the particle with respect to the one and the motion of the particle with respect to the other, these two things can be related using Galilean transformation or Galilean relativity principle, okay. We also said that the basic laws of motion, the basic laws of mechanics, okay, that should not be changed if we switch from one inertial frame to the other, okay. And again we said that just using the fact that for a free particle, the space and the time as both are homogeneous with respect to an inertial frame of reference, that's why for a free particle, this homogeneity of space and time and the isotropy of space can be incorporated into the form of the Lagrangian of the freely moving particle. Because in some sense, if you think that the particle which is moving freely, we showed that this is moving with a uniform velocity, so that particle can also be somehow thought to be an inertial frame itself, right? So you see, that is a back and forth logic. That in this way, so basically, when we started by saying that the space and time homogeneity and the isotropy of time should be incorporated in the free particle Lagrangian, then we did not understand that the free particle can itself be an inertial frame of reference. But when we concluded finally that free particle actually has the property of constant velocity, then finally we can associate that with another inertial frame of reference. And finally we showed, or we finally realized, that what we started with was not an illegitimate approximation, okay. So till now we can conclude that free particle Lagrangian should be the Lagrangian which is a function of v square or mod of the velocity square only, okay. So whether this is mod of velocity or mod of velocity square, this is the same thing. Now think that k prime and k both are inertial frames, and k prime is moving with an infinitesimally small velocity epsilon with respect to k frame, okay. So the velocity of a free particle v in k frame and that in the k prime frame which is given by v prime, both are related by simply this formula which is coming from Galilean transformation, which is given by v prime is equal to v minus epsilon, simply, right? Just the vector difference, okay. Since the equations of motion must have the same form in two inertial frames, okay, then the both Lagrangian should give the Lagrangian of a free particle in k and that the same free particle in k prime frame should give the same equations of motion, okay, because the equations of motion should not depend on which inertial frame of reference I am in, right? And that's why those two Lagrangians should at best differ from one another by df dt, where f is a function of r and t, coordinate and time, right? Now if you write that the Lagrangian of the free particle in the prime frame as Lagrangian LF prime, which is nothing but LF of V prime square. Okay, basically we know that for any system, okay, for any frame of reference, if the particle has a velocity v in that frame of reference or with respect to that frame, then it would, the corresponding Lagrangian will be LF v square. Okay, so where this is the velocity is v, this is LF of v square, LF of v square, and where this is v prime, this is LF of v prime square, right? So this is basically the Lagrangian in K prime frame, Lagrangian of the free particle, and that you can always write as the Lagrangian of the the same particle in K frame plus a df dt, which I just said due to symmetry transformation, right? Again, by expanding v prime as v minus epsilon, you can also write this is also equal to LF of v minus epsilon whole square. Now, as epsilon is infinitesimally small, that is actually the interest of taking at the first step the infinitesimally small relative velocity. Then we can just expand this function, okay, up to the first order of epsilon, okay, where you can write LF v prime square is nothing but LF of v square minus del LF del v square times 2 times v dot epsilon. There should be a term with epsilon square which we neglect. Okay. Now, in order that this extra term, this minus del LF del v square to v dot epsilon be a df dt, we have to note that already v is nothing but dr dt and epsilon is a constant vector. Now, del LF v square by del v square, this is a function of v square, right? Simple. Or can be a constant. Okay. Now I can write, since LF is only a function of v square, I can just change all the dels to d, and I can write this is nothing but minus dLF v square by dv square, which is another function of v square, gv square, let's say. So this extra term now can be written as 2gv square, okay, ddt of r dot epsilon, because epsilon is constant, so it can be taken inside. So ddt, so 2 v dot epsilon can only be written as ddt of r dot epsilon. So this is already a function of, this is already a ddt of a function of r and t. T is not there, but r at least. Okay. Now I have this extra term. Now think that if this is a function of v square, this is not actually never possible to write the whole thing without adding or subtracting anything as a ddt of r vector and t, unless this does not have any v square dependence or this is just a simple constant. Okay. And if this is true, then for that we can simply write that dLF v square dv square is constant. So LF v square will be linear to v square. Okay. If LF v square is linear to v square, then we can simply write that LF v square is equal to some constant time v square. Okay. And we can write, of course, that there is a constant of integration, which you can just say that when the v square is 0, then the LF is also 0. You can impose that condition, then the arbitrary constant of integration will go away. And you say, now let us choose this constant of proportionality to be half of m. I don't know still what m is, but I just write half of m. Then LF is equal to half mv square. I also suppose here m is greater than 0. Why I am coming to that point? Okay. Now if someone using her or his previous knowledge of kinetic energy or something can relate this to the kinetic energy what is obtained from Newtonian mechanics, can easily see that this constant is half times the usual mass of the particle. Okay. So the aforesaid form of LF basically satisfies Galilean relativity for an infinitesimal relative velocity epsilon. Right? We now will verify whether this also holds good for a finite relative uniform velocity v or not. Now we know the exact functional form, that is half mv square type of thing. Now we will cross check whether instead of epsilon, if I write some finite v constant velocity, relative velocity between k and k prime, can I also have a symmetry transformation for the Lagrangian always? Well, the good news is yes, you can always write, because then LF prime will be half m v minus capital V whole square. Capital V is a finite constant velocity or uniform velocity, which is the relative velocity between, of k prime with respect to the k. Then you can simply write this is equal to half mv square minus mv dot v plus half mv square. Now you see that v is constant, capital V. So this is dr dt. So we can write this as minus ddt of mr dot v. And this one is a total constant. So we can write this as also as a ddt of minus half of mv square times t. Right? A simple thing. So finally you are given a function which is a function of r and t only, and ddt of that function is the difference of these two Lagrangians. So we are done. So basically, whether there is an infinitesimal relative velocity or a finite relative velocity between two inertial frames of reference, they will always give you the same laws of motion if we take the form of this free particle Lagrangian as half mv square, where v is the velocity of the particle in that reference frame. Okay. It is therefore reasonable to accept LF as half mv square to be the universal form of free particle Lagrangian in any inertial frame of reference. That's very important. It should be in any inertial frame of reference. Okay. Okay. Now, m is called the mass of the particle, as I just said. The additive property of Lagrangian now simply says that if we are now to determine the Lagrangian of a system of non-interacting free particles, let's say n number of free particles in an inertial frame of reference, then the Lagrangian will simply be the sum of all the half mi vi squares, and will simply be given as half summation over mi vi square or mi ri dot square. Okay, where ri is the position vector of the particle, instantaneous position. Okay. Now, since the Lagrangian can be multiplied by an arbitrary constant without affecting the equations of motion, basically no change in the motion of the particle would be perceived by an arbitrary choice of units of mass. That means you can simply write your mi as 10 mi or 100 mi or 1 by 10th mi, whatever be its the thing. Finally, the Lagrangian would not change, because you are multiplying every sub-Lagrangian or single particle Lagrangian by the same constant, as we just discussed in the previous lecture, right? So that simply says that we are choosing different units of mass, and finally that would not change the Lagrangian, and so no change in the dynamics. However, remember that the ratios of the masses, they are very important. They should not change here. Okay, so let's say m1 by m2, m2 by m4, m3 by m1. These ratios, if they change, then there would be a problem. That means that there is a change in Lagrangian other than the multiplication by a constant factor. So this Lagrangian is not the same Lagrangian qualitatively, okay, to this previous Lagrangian, Also quantitatively is not. Quantitatively is, I mean, that's also, I mean, quantitatively the Lagrangian is always different, even if you multiply this by a constant factor. What I am saying, in the second case, it's both qualitatively and quantitatively different, and the motion will change. Okay, that you have to understand. Now, although we have to remember that in the general proof of this principle of, I mean, the Euler-Lagrange equation using the calculus of variation, we used the principle of stationary action. We said the action can be least, most, or greatest, or stationary. Basically, in the next part, we will justify, okay, we will practically justify that why for physical or mechanical systems we should only have least action. We will see that. For that, we will use this trick. We write the action integral for a free particle, which is given as an integration over from t1 to t2 half mv square times dt, right? You know that for the real trajectory, this is nothing but this times t2 minus t1, because v is uniform on the real trajectory. But now we will try to vary this action on different paths, and we will see what happens. If we vary, then we have to vary virtually. That means we have to take recourse to this second parameter, the smallness parameter alpha, and we write an arbitrary x, I mean x dot, as the proper x dot on the real trajectory plus alpha times some eta dot t, where eta t is another function, okay, of t, if you remember, okay, because of these definitions, okay, t is the intrinsic independent variable, okay. Now we are writing the whole thing as, so the total, so the general action variable, okay, action integral on an arbitrary path, which may or may not be the real path, should be half m integration over t1 to t2 x dot t plus alpha eta dot t whole square dt. We now take the differentiation, so this is a function of alpha only basically, because it's already integrated out over t. So this will simply be written as d sf d alpha, which is nothing but this one. You just take 2 out, and so 2.5 will go away, and this part will be there, and then you are just doing partial, I mean you are doing differentiation with respect to alpha. So basically this will be, so the only thing is that if you are confused with that, so here you can always write dd alpha, because this is before integration, I mean after integration. But when this dd alpha will enter into this integration, then if you remember the Leibniz rule, that will enter as del alpha always, okay, and then del alpha will just act on this term, okay, and that will simply give you eta dot t, okay. Now we know that for that to be 0 at alpha is equal, sorry, this is alpha is equal to 0, we have this is equal to 0, right? We should know that this is 0 at alpha is equal to 0. That is the real path, real trajectory of evolution, right? And if this is true, then we can say that the only possibility if this is 0 is if you just do from here to here another integration by parts, here to here another integration by parts, finally you can see that eta can be arbitrary, right? So the only possibility that this is identically 0 is x double dot is 0, which simply say x dot is a constant. That means we must have on the real trajectory the velocity will be a constant thing. That's completely consistent with what we are doing. Now what about the second order derivative of this? So the second order derivative is this d2sf d alpha 2. You have to integrate it once again, and you will have this m integration t1 to t2 eta dot square dt, right? And this is always positive because m is positive, okay, so this is positive because I supposed that m is positive, okay. Just now forget about m. What about this part? What about this part? This is positive because eta dot square t is positive and dt is integrate. So this is a support. I mean, this is the integration limits are both in the positive. I mean, the two positive limits are there, t1 and t2. So they must be positive. Okay. If they are positive, then if the only way that this can be negative is that if m is negative, or if this is positive, then m is positive. So basically m will determine the sign of this second order derivative. So basically from our experience we know from experimental facts that m is greater than 0. That means d2sf d alpha 2 must be positive. That means that sf will have a minimum. So the real trajectory will be the path of least action and not the greatest or most action. Okay. Now in Landau's book, as I said in the discussion forum, that you can see the thing is done in the other way around. He said that he assumed that the principle of least action is correct and not the greatest action or anything. And from that he argued that mass cannot be negative. That's also possible. But for me, I think that it is somehow much more interesting because like whether mass is positive or not, that we can always know from experimental facts, whereas whether the principle of least action is correct or not, that we cannot really determine from our everyday experiments or experiences. Okay, so I mean, that's all about this the Lagrangian of the free particle. Okay. So now in the second part, in the second subpart of the this lecture, I will talk about the Lagrangian for a system of particles which have non-zero interaction. Okay, thank you.